Welcome back. I didn't forget the discussion of the exam, but I want to make sure that we first cover enough of neural networks to start working on your assignment today, which will be out today. So we'll do enough of that, and then we'll come to the exam. Gotcha. Now you're here anyway.
For the rest of the semester. One day you'll tell us about the exam.
In fact, I can just say that every class we're going to flip a random coin, not necessarily a fair coin. Okay. We're talking about neural networks. I think you all know where it's heading. It's heading towards big neural networks that do fabulous things with a very deep understanding. But we have to start with the fundamentals. And the fundamentals remain for all of machine learning, at least in my mind. This is sort of my list, not a agreed upon list. Question of hard bias, soft bias, and optimization. Hard bias and soft bias together are inductive bias. The boundaries between them are sometimes arguable. But I like to make the distinction between a hard bias, which is what are you allowing yourself to consider, or what is expressible in the framework you're considering, and then a soft bias, which usually boils down to a preference, a ranking, or an optimization criterion. That's also a preference. So argmin, the argmin formulation comes in here. Argmin or argmax, some kind of optimization criteria, minimizing loss, minimizing the sum of the loss plus a regularization. All of that come under soft bias. And now, once you determine your hard bias and your soft bias, now you have an optimization, well-defined optimization problem. But now the question is computational. Can you solve it? Can you find the true optimal? And can you do it computationally efficiently or not? And that's the third question. What is your search algorithm or your optimization algorithm? Okay? The holy trio. 1, 2, 3. All right. Let's revise what we know. Linear unit implements a linear function, right? All linear functions and nothing else. Let's talk a little bit about what a linear function is. I mean, you can express it algebraically as the dot product of the coefficients and the covariates. Beta I, xi, right? Sum over I. One other way of understanding it is if you think of n covariates, let's say p covariates, think of a p-dimensional space, Cartesian space. And the set of p plus 1 betas, or parameters, or weights, determine a hyperplane of dimensionality p minus 1 that has a certain orientation in the space. And that hyperplane separates the space into two half spaces. You're not sure? You agree? Okay. So let's draw that. Beta x is sum of beta I xi. I goes to start with, well, goes from 0 to p. The 0 corresponds, of course, to 0 being 1, and beta 0 is your offset. So let's see how that vision works in the simplest case of, not the simplest, but a simple case of 2 dimensions. So when p equals 2, the space can easily be visualized as x1 and x2. Infinite 2-dimensional Cartesian space. Setting the function, first of all, you have 3 parameters. You have beta 0, beta 1, and beta 2. Beta 1 and beta 2 together determine an orientation of a line. Beta 0 determines its offset from the origin. So if beta 0 was set to 0, beta 1 and beta 2 together would determine a line that passes through the origin. With the addition of beta 0, the line can be shifted. So let's say you have a single line here, x1, x2. Say the line goes like this. Now, what is the relationship between this line and the linear function that is described by the betas? The answer is that it defines, this line defines a direction in the space, the direction perpendicular to the line. And the function y equals beta x measures the distance from the line in this direction or in that direction. One of the sides is considered the positive side, the other one is the negative side. A linear function can be thought of as defining a p-1 dimensional hyperplane. In this case, p-1 is one-dimensional, a line, and giving us an answer the distance, the perpendicular distance from that line. So if you're here, you drop a line perpendicularly to here, and this distance, -10 or whatever it is the answer from the function. As you change b0, the line moves up and down. As you change b1 or b2, the line changes its angle. You notice that there is a degree of freedom here with b1 and b2. That means you have an extra degree of freedom. How does it play here? If I multiply b1 and b2 by the same constant, then the angle would, the slope would remain the same. You would need to change b0 as well. So for every multiplication of b1 and b2, if you want to keep the same function, you would need to change b0. Is that true? Yes, I think so. Go ahead.
I'm confused. I would think that with two parameters, we would create a plane, right? Because wasn't y a third dimension? So wouldn't we have a three-dimensional space, and then we cut a plane through it if you have two covariates?
Well, you have two covariates. So the input space is two-dimensional, right?
Okay. So you're drawing a line through the input space.
Right. We can go back. We can go down to p equal 1. P equal 1. The input space is just a single line, x1. The function is y equals beta 0 plus beta 1 times x1. And what you're doing is the p-1 dimensional is a point, which in this case would be basically the b0 point. And the function tells you how far you are from that point. Let's think of a very high dimensional space. We can't visualize it. If you have a p-dimensional space, well, let's think of a three-dimensional space. If you have a three-dimensional space, a linear function in three-dimensional space determines a flat surface, a two-dimensional subspace that could be at any orientation and any angle in that space. That orientation has 2 degrees of freedom, but it's controlled by beta 1, beta 2, and beta 3. And then there is an offset parameter. The linear function determines just the orientation. I'm sorry, this determines just the orientation and the offset. The linear function tells you specifically what the answer is, and the answer in the case of a linear unit is the distance from that plane, okay? The perpendicular distance for the plane. We're going to look now at the perceptron, and there the definition of the hyperplane is exactly the same, but the answer is different. The answer of a perceptron is not how far are you from the hyperplane. The answer is which side of the hyperplane are you on. It's a binary answer, 0 or 1. Are you on this side or are you on that side? Which is why we say that perceptrons can express linearly separable functions. All linearly separable functions consider a linear unit and a perceptron that have the same betas, exactly the same betas. So the first step of linear summation is the same. Linear unit gives you the answer, but doesn't change it, which corresponds to the distance. The perceptron doesn't care about the exact value, it just wants to know if it's greater than 0 or less than 0, and gives you as an answer either 0 or 1 or -1 and +1, two values, one corresponding to being on one side of this and the other corresponding to being on the other side of it. So if I use a straight arrow to indicate the linear unit, I would use a positive sign on this side and a negative sign on this side to designate the perceptron. You can see it also in the transfer function. Here's the transfer function of the linear unit. Here is the transfer function of the perceptron. We said that the expressive power of a network of linear units is unfortunately no greater than this, and therefore we're no longer not interested in anything else to do with it. Going back to Q2, we decided to use here mean squared error. We don't have to. And when you use mean squared error, it turns out this is a convex problem, which means you could use gradient descent and be guaranteed. I'm sorry, let me start. You can use the solution we said is you could just use the standard OLS solution. It means algebraic solution. Which means we have a closed form solution, and as long as the problem is well posed, the matrix is full rank, we can find a solution immediately with some computation, as we discussed when we discussed linear algebra. But we also said that because this is convex, we can also use gradient descent as an alternative way of going about it. And for gradient descent, I described the general gradient descent algorithm, and I don't know if I showed you the formula for, I think I did, how it applies to a single linear unit. So this is mean squared error. This is the definition of mean squared error over the training data. We went through this, and what I want to show you here is just the result here. The result is important because we're going to compare it to the result for something else. I don't have room there, so well, let me try to copy it here anyway. The gradient of the error with regard to each weight has the form. Let's suppose, for simplicity, there's just a single training data. Suppose we're applying this gradient descent for one training example at a time. Then we don't need the summation, and we end up with the error. This is the error, the truth minus the output, times the negative of the corresponding covariate. So the change in the weight, delta Wi, would be, if you remember, gradient descent is negative eta times this partial derivative. So it'll be negative step side times this derivative, and this derivative would be t minus o times negative xi. So negative and negative can go. What I want you to keep in mind is this formula. The simple formula for gradient descent for a linear unit is the change in the weight is proportional to the error times the value of the covariate, whose weight we're talking about. All right, now we're talking about perceptrons. Now let's switch to perceptrons. Our hard bias is all linearly separable functions. It's very closely related to bias for linear units, but it's speaking a different language because it's a bias among classifiers, all classification functions, rather than all regression functions. Okay, so they're not exactly the same thing, but they are in principle the same thing. They're both off of the same hyperplane. What optimization criteria can you use with a classifier? What should you use with a classifier? Suppose you want to use a single perceptron to classify a bunch of training data. What optimization criteria would you use, please? Number of misclassifications, right? Or percent of misclassification. We'd call it percent misclassification. Thank you. Percent misclassification. You don't have to. You can also declare if the binary classifier two labels are 0 and 1, you can declare the correct output as 0 and 1. And if you have a regressor that gives you back a continuous number, you can do mean squared error from those 0 and 1. But since the perceptron doesn't give you a continuous number, it gives you either 0 or 1, all you can do is count when it's wrong, when it's right. So that's percent classification. Now, what are we going to do about search? A perceptron learning, perceptron training, is very similar to training of a linear unit in the sense that you have the same parameters, beta 0 through beta p. And you are adjusting these parameters to optimize your criterion. So you're searching the same space, but your criterion is different. Your criterion is discrete. In fact, I should, instead of percent, I should stick with your original suggestion of number of misclassified. Number of misclassifications. You have a finite amount of data, 1 million training examples, and you're trying to minimize the number of them that you get wrong with the classifier. There's a big difference here because this is a discrete measure, a non-continuous measure, a discontinuous measure. You make a small adjustment to the hyperplane by changing one of the betas, and one of the positive labeled point moves to the other side, or one of the negatives moves to the other side. Or you make a small adjustment and nothing moves to the other side. You make another small adjustment and nothing moves to the other side. Then you make a tiny adjustment and something moves to the other side. So the error function is not a continuous function of the parameters. That's a big difference. In the linear regression or linear unit case, if you rotate the hyperplane by a little bit, by changing one or more of the betas by a tiny amount, you're guaranteed that the mean squared error measure would change by a little bit. So this is a continuous function of the parameters. Parameters are the betas. This is a discontinuous function function of the betas. Big difference. Yeah?
Professor, yesterday when we were discussing the linear unit case, we had two steps. One was linearly combined inputs and the second one was transfer function. You just said that the transfer function basically is not doing anything, right? But in this case, how does that second step change because the transfer function is doing something?
Right. So the transfer function is doing something, and unfortunately what it's doing is discontinuous. So that results in the fact that the error rate here is a discontinuous function of the inputs. Maybe I don't understand your question.
Just want to understand, how do we represent the step 2 now?
How do you present step 2 now? It's this picture. The total beta dot x, which is the net, is the input into this. This is the net. Beta dot x. And if it's above 0, the answer is 1. If it's below 0, the answer is 0. That's the transfer function. Okay, so we have a search problem. We're trying to train a single perceptron to do linear separation or linear classification. We can't use gradient descent. Why can't we use gradient descent? Yeah? It's discontinuous. Let's see the whole change. Gradient descent means you have to start by finding the derivative of the error with regard to any one of the weights, or in this case it's beta. The error itself is some summation over the training data of the truth d minus output d squared. The truth is a constant. The output is not. Actually, we have it here. If you go through this process, you get to this point. You get to this point, the derivative of O sub d. And in the linear case, it's very simple. It's just the derivative of this dot product, which becomes x. But in the perceptron case, it's not. It's continuous, and you can't take the derivative. Okay? That's why we can't do gradient descent. We can do something that looks like gradient descent. It's called the Perceptron learning rule. And its form, which is very similar to the form I wrote there, so I'll write it here. Perceptron training rule. Delta Wi is some eta times t minus o times xi. It's pretty much identical. See, this became a plus and this became a plus. It's not plus x, it's times the positive xi. This is completely identical. You define a step size. You cycle through the data. You don't have to sum all of the training elements. You can do it one step at a time. Same is true for gradient descent. You can do that one step at a time. And you apply the rule as if it were gradient descent. Now here's what we know about this algorithm. This algorithm was already developed in the 60s. We know that if the training examples are linearly separable, the algorithm will eventually find the separating hyperplane. Namely, it would get to an error of 0. 0 error, it classifies everything correctly. What's the equivalent with linear unit? It says that if the points are really form a linear function, the OLS algorithm will find that linear function. What happens in the OLS case when it's not a clear linear function? It finds the least square deviation from the points, right? It finds an optimal compromise in some way. The perceptron learning algorithm will not do that. What the perceptron learning algorithm will do, if it cannot find a solution, is it will cycle forever. It will not stop. It will keep on moving and moving points from one side to the other and then other points from one side to the other and so forth. So it's an algorithm that doesn't terminate. Unless the points are linearly separable. If they are linearly separable, it will terminate. But it may take a very long time to do that. It may take an exponential amount of time to do that. The question of whether some training examples are linearly separable or not is asked many times, comes up in many, many areas, in engineering, in lots of areas. If the points are in two-dimensional space, it's very easy to answer it by kind of looking at it. This is linearly separable. This is not linearly separable. You can kind of look at it and do this with your hand and decide if it's linearly separable or not. But when the points are in 50-dimensional space, it's actually a very non-trivial question. An important but non-trivial question. You can throw the perception training algorithm on it. You start the betas with some random values, and then you iterate through all the betas using the simple update rule. And you say to yourself, if it terminates, I know it's linearly separable. If it terminates in a reasonable time before I come back tomorrow, I know it's linearly separable. But if it hasn't terminated, then I don't know. So there are other ways of trying to answer the question of whether points are linearly separable or not. None of them are nice polynomial. They're all exponential in the dimension, in P. Not in N. Not in the number of data points. So it's one of these problems. Linear separability is one of the problems that are kind of semi-hard. It's doable, but it's exponential in the number of dimensions. If the number of dimensions is 50, you're out of luck. But that's the best we can do with the perceptron so far. So linear separability is important, but we may want to move to other highly nonlinear functions and learn them. So the next thing we might want to do is a network of perceptrons. Just so that we all understand what a network of perceptron does. It's a network of neurons. Here are inputs. The inputs could be discrete or continuous. Assuming we have multiple layers, the first layer, these are all perceptrons. So I'll put a little step function next to them. I'll just put one here. The outputs from these guys are all discrete now. So in a perceptron network, the input may be continuous, but as soon as you move into the network, the first units, their outputs are discrete because they're perceptrons. And they go into perhaps another layer. And then after so many layers into maybe a single output. And the single output is also discrete. So it's either 0 or 1. Lots of weights. What can this implement? Since the output is 0 or 1, of course it implements only binary classification. But can it implement all binary classifications? The answer is yes. Because of the nonlinearity of the step function, we've broken away from the curse of linearity, or from the closure of linearity. We can now represent pretty much any nonlinear classifier, as long as we allow ourselves enough units. In fact, there are results that show that you don't need many layers. You can represent any continuous function with a single layer, as long as it has enough units. And you can even represent discontinuous functions to arbitrary accuracy if you allow yourself 2 layers. So there's a neat little mathematical result that says you don't need more than 2 layers, and if you're only interested in continuous, actually, let me take that back. Since this is a classifier, we're not talking here about continuous functions. Let's just say that 2 layers will definitely be enough, and maybe even a single layer would be enough. But the catch is that the number of units that you may need may be exponential in the number of inputs. In fact, let me prove to you right away that you can implement any classifier with a single layer. All I have to show you is that perceptrons can implement ANDs and that they can implement ORs. Okay? So I can show you that they can implement any binary classifier over binary inputs. So if you assume that these are all binary, you can represent any binary classifier as an OR of ANDs. So it'll be something like x1, x5, x9, or, so this is AND, x1 and x5 and x1 and x9, or x1 bar, x2, x3 bar, or, and so forth. You can represent any function as an OR of ANDs, and then you can use each one of these to implement the ANDs, and then use this to implement an OR. How do you implement ORs and ANDs? Let's look at it in 2 dimensions. If these are negative 1 would be, your points would be here, -1 and +1. By passing a line this way, or let me make it 0 and 1 so it'll be the same language as the output of the perceptron. Here are the 4 possible inputs that are x1, x2 binary, 0 and 1, 0, 1, 0, 1. This line, with this orientation, corresponds to an AND. The same orientation, but passed here, will correspond to an OR. Is that clear why this is an AND? Because it says yes, or it says 1 only when both x1 and x2 are 1. And it says 0 otherwise. So linear decision boundaries are generalizations of sort of binary functions. If you look at the functions only on the vertices of a hypercube. So this is a little digression. The take-home message is that we don't have much bias here. Any binary classifier with large enough network, or I would say more specifically with enough units, enough neurons. And I would say 1 to 2 layers are sufficient. So this is now a little bit like a decision tree in the sense that the mechanism itself does not restrict you. There's no hard bias inherent. the hard bias will be introduced by reducing the size of the mechanism. As if you restricted the decision tree to no more than a certain number of nodes, here, if you restrict the network, you restrict the topology to no more than so many neurons or units, now you do have a hard bias. Here we will use the same criteria as here, number of misclassifications. And it is a discontinuous function. Of the betas. And now we come to the search problem. And again, we cannot use gradient descent. Because the error function is discontinuous in the parameters. And we can't use the Perceptron training rule because the Perceptron training rule was the heuristic that worked for one perceptron, and it's not guaranteed to terminate anyway. And now we're stuck. We don't know of a way to efficiently train a network, a fixed topology network of perceptrons to minimize the error over the classification error over training data. No known efficient algorithm so we're increasing our expressive power, but we're making it, by doing that we made it difficult for us to find a solution. We're willing to use gradient descent, even though it's not guaranteed to give you global minimum, but we're willing to use it, but we can't use it here because the error is discontinuous in the parameters. And the error is discontinuous in the parameters because the transfer function is discontinuous. That's the link that makes it discontinuous. So what should we do? We want a transfer function that is powerful enough so that when you put together a network, you get very strong, wide expressive power. You can express many functions. But we want to do gradient descent. Any suggestions, or did I lose you completely today? You're just here for the exam, aren't you? Yeah.
Use a continuous function that's an approximation.
Thank you. Thank you. Use a continuous transfer function that is an approximation of the step function, or that is otherwise nonlinear. Use a continuous nonlinear transfer function. Okay? We tried a linear transfer function, no good. We tried a step, nonlinear, but step function, no good, because it's not continuous. Let's try something that is both nonlinear and continuous. In fact, let's try something that looks as much as possible like a step function, because we like the step function. So let's try something like this. This is the step function. Let's smooth it out. Let's do something that looks like this. It looks like a smooth step function, smoothed out step function. There's a function that looks like that. It's very easy to write down. It's called the sigmoid. Here's the transfer function. It's a function of the net. It's 1 over 1 plus e to the negative net. The value of this function when net is 0, e to the negative 0 is 1, 1 plus 1 is 2, 1 over 2 is half. So it passes right through the half point between 0 and 1. As net becomes extremely large, e to the negative net goes to 0, and this becomes 1 over 1. So the asymptote here is 1. As net becomes extremely large negative number, e to the negative net is e to a very large number. It goes to infinity. 1 over infinity goes to 0. So the asymptote on this side, it goes to 0. So this function has the property that it asymptotes to 0 on the left, to 1 on the right. It passes through the half point. In fact, it's symmetric, or rather anti-symmetric. And it's continuous, which means we can take its derivative. And when you take the derivative of this thing, you get a nice surprise. The derivative of net with regard to its input, is simply net itself times 1 minus net. It's kind of a nice bonus. It's not just the continuous and differentiable, but also the derivative is very simple.
Ronnie, I think the net should be a sigmoid function.
The net should be?
Sigmoid net. 1 minus sigmoid net.
Oh, 1 minus sigmoid net, sorry. Both of them?
Yep.
Sorry. My bad. Thank you. Yeah, it's sigmoid over sigmoid. Yeah, thank you. So we're going to use this as our transfer function, and when we do that, the unit is going to be called a sigmoid unit. This is the most popularly used transfer function in neural networks, but it's not the only one, and it doesn't have to be the only one. There are many others you can use. The important thing is they should be continuous, so you can do gradient descent. They should be nonlinear. And you probably also want them to be monotonically increasing. The reason is, or monotonically decreasing, but they should be monotone. The reason is, if you have a transfer function that goes up and down, when you do gradient descent, you can get lodged here in the local minimum or local maximum. So as long as you stick to monotonically increasing continuous nonlinear functions, there's no particular benefit to this function except that the derivative is very nice. Question? Or no? Okay. So this is going to be called a sigmoid unit. First, we look at the single sigmoid unit. What is the expressive power of a single sigmoid unit? Question.
Is it better to have a function that's flat between 0 and 1, or that's more like Perceptron?
Is it better to have a function that is flat between 0 and 1?
Or is that goes up quickly like Perceptron?
You mean a function that is flat for a while and then starts going up? There are implications for functions that are, if flat, and you end up somewhere in the middle of that flat, there's no gradient, so it will not move you out of there, right? So you probably don't want anything that's flat anywhere. Which also means that in this kind of sigmoid behavior, when you're here, there's a very, very gentle gradient up. You would be moved up, but very, very slowly. Whereas here, you would move much faster. So that could be both a curse and a blessing. In the sense that, well, we will talk about it later, as you push the points away from the center, they're stable, but they're very hard to change. So you can think about it, now I'm just hand waving, you can think about this as like where all the action is, and this is where it goes to rest and not be bothered. Let's go back to the question of expressive power of a single sigmoid unit. A single sigmoid unit is in some sense very similar to a linear unit and very similar to a perceptron. It just does beta I times xi, summed over I, right? It's the question of what it does with it at the end. So a single sigmoid unit defines a hyperplane, just like the linear unit and the perceptron. They all define the same hyperplane. The question is, what do they do with that hyperplane? A linear unit gives you back the distance of your point from that hyperplane. A perceptron gives you back, are you on this side of the hyperplane or on this side of the hyperplane? And a sigmoid gives you something in between. It gives you back a number between 0 and 1 that if it's more than half, it's on one side of the hyperplane. If it's less than half, it's on the other side of the hyperplane. And you can determine the distance based on that number. But it's as if you took the entire distance from negative infinity to positive infinity and distorted it, squished it into being between 0 and 1. It's not as if, it's exactly what a sigmoid does, right? So a sigmoid, all three of them can represent the exact same hyperplanes. So as a result, what I could say here is it's also all linearly separable functions. Kind of. It's all linearly separable. Now we're not talking about separation into positive and negative. We're talking about assigning actual values. But you can think about it as creating a margin such that if you're far enough away, the answer is very close to positive 1. If you're far enough away this way, the answer is very close to 0. And if you're here, it's like you're in the uncertain area. This is the kind of thing that a single sigmoid unit can do. Not very interesting, not very different than a single perceptron or a single linear unit. What's going to be our optimization criterion here? Well, a sigmoid is a regressor in a sense. It produces as an output a continuous number, but that continuous number is bounded between 0 and 1. Which means you don't want to use it to do general regression. You can't get it to give you numbers outside that range. You could use it to do logistic regression. And in fact, this is what logistic regression does. You could still impose any kind of, within learning outputs that are between 0 and 1, you can decide on different kinds of error measures. You could use mean squared error. Or other. But you can only learn functions into the range 0 to 1. What about the search? You can do gradient descent here because sigmoid is continuous and differentiable. And with a single sigmoid, you will find the optimal answer. This is what logistic regression fitting procedures do for some suitable definition of the error. The one difference is that one difference from linear units is here we have a closed form solution. Here we don't have a closed form solution. Gradient descent is an iterative procedure, not a closed form solution. Now we're finally ready to go to a network of sigmoids. And a network of sigmoids, as you can guess from a network of perceptrons, is a universal approximator. It can approximate any function, and now that we're talking about sigmoids, it's continuous functions. Any continuous functions into the range 0 to 1. Any function into 0 to 1 with sufficient weights, with enough weights. I'm sorry, with enough units, enough neurons. And here is the result that I mentioned earlier by mistake for the perceptrons. If you have a single hidden layer, as long as it's large enough, you can implement any continuous function into the range 0 to 1. And if you want to implement also discontinuous functions with arbitrary level of accuracy, you can do it with 2 layers. So you don't need a very deep network, but the network might have to be very wide. And the number of neurons that you need in the hidden layer may be exponential in the number of inputs. But may require exponential number of units. What objective criterion, what optimization criterion should we use with training such a network? Just like in the case of a single perceptron, it's up to us. We could use mean squared error. We could use other measures. And people have used a variety of measures. The important thing to note is the output is bound between 0 and 1. By the way, when I keep talking about between 0 and 1, you have to realize that if you really want it to be between 27 and 28, or 29 and 35, you can do that too. You can map it, right? You can map the sigmoid to any finite range. We use 0, 1 just generically. So this could be mean squared error or other. Into 0, 1. And what do we do here? What do we do here? Gradient descent, finally. Gradient descent. So we have reached our destination. We're going to use a network of sigmoid units, namely units with the transfer function that's a sigmoid. And we're going to use gradient descent to train it. To remind you of the limitations of gradient descent, it is not guaranteed to bring you to the lowest possible minimum of the error. Right? It could very well get stuck, and it often does get stuck in the local minimum. Now we have another problem. Let me write down the definition of gradient descent. Gradient descent means you start with the weights being some random values, and then you go through iterations, and in each iteration, for every weight, you change the weight by an amount that's negatively proportional to the derivative of the error with regard to that weight. You do that for all the weights together, and that effectively moves you in the direction of the gradient, in fact, opposite the gradient, because it's a negative sign, so that you go down the surface of error. Now let's imagine a typical network of sigmoidal units. Each one of these lines is a weight, and we need to calculate the derivative of the error with regard to that weight. What is the error? The error is known after we calculate the output of the network, and then we look at the correct output versus the actual output. The actual output is a function of all the weights. We take that, we square it, and this is effectively the error. Now, what would be the contribution of, say, this weight the weight along this edge to the overall layer? The answer is it would have many contributions, because this weight determines the output of this unit, and the output of this unit gets multiplied by this weight when it gets sent here, and by this weight when it gets sent here, and by this weight when it gets sent here. So if I make a small change in this weight, it affects the output to all of these. And in multiple layers, it would affect many, many more. So that one change in one edge, in the weight of one edge, will propagate up along many possible paths and will affect the error in many different ways. So if I were to write down the explicit expression for the derivative of the error with regard to this weight, it would consist of many, many components having to do with having come through here, and having come through here, and having come through there. And in fact, the number of components is going to be exponential within the number of layers. So even though conceptually it's very clear what we want to do, we want to find the partial derivative with regard to every one of the weights, there's a computational challenge of how do we do that in a computationally feasible way. The answer is dynamic programming. How many of you are familiar with dynamic programming? Okay, good. So at least those who are know that dynamic programming deals with situations where you have to sum over an exponential number of paths, but because these paths share components with each other, and because the paths don't have memory, they're amenable to a polynomial solution. And this is exactly what we do here. The algorithm that we're going to be using is called the backpropagation algorithm, and it is nothing more than dynamic programming applied to calculating partial derivatives. So let me give you first the full picture of how backpropagation works, and then we can go to some slides of the details. You have some training data. You have covariates x1 through xp, and you have a y. You have training data that's x11, x21, xp1. I want this to be the covariates, so no, I'll make it x12, x1p, and then y1 all the way to xn, x1n, xnp. Make up your mind, Roni. 1p, np, 11, np, so n1. So this is just a convention, but I will use the first index for the index over the rows, which are the training examples, and the second index over the covariates. So this is exactly the same as in linear regression. Here you have yn. We're going to initialize the network. Remember, there are three decisions in a network: the topology, the transfer function, which could be different for different units, but for simplicity, let's say one transfer function, and the weights. For this algorithm, we're going to fix the topology and fix the transfer function. So topology is fixed. We'll talk later about the difference between different choices of different topologies. The transfer function is going to be fixed, the sigmoid function, and we're only changing the weights. And the way we're changing the weights is we're going to initialize the network with some weights, random. And when I say random, you have to actually specify how you choose randomly. I'm going to choose maybe uniformly in a small range around 0. Or maybe as a Gaussian small range around 0. The important thing is that these are going to be small weights for the most part, and they should not all be 0, and they should not all be the same. They should be different. We'll talk later about why. But this is our initialization, and then The first thing we're going to do is calculate the error of the network that we define that way. Once we fix the weights, we define the function. Once we define the function, we can pass the input to the function and compare it to the outputs. This is what we call the t values. In fact, I shouldn't call them y, I should call them t1 through to tn. These are the truth values. We're going to feed these into the network. So we're going to take the first one, feed it at the bottom of the network, feed the signal forward, so it's called the feed forward step, until we get an output, for simplicity a single output. That output, O1 compared to T1, square it. That's our error on the first training example. We repeat it for all the training examples, sum all the errors. Now we have our error measure. Now we need to calculate how this error depends on each weight in the network. Now we need to calculate this thing, and we're going to do it going backwards through the network. We're going to first calculate the dependence on of the error on these weights, and then we're going to use a recursive quantity in each one of these units to use it to calculate the dependence of the error on these weights, and then move to the next layer down, all the way to the last layer of weights. Once we calculated the derivative of the error with regard to every one of the weights in the network, we will apply the gradient descent rule for all of them using the step size. This will change the network somewhat. And now we're going to start the process all over again. Given the new set of weights, plug in the values, propagate them forward, calculate the error, go through the process of going back. So let me show you now the derivation of the gradient of the backpropagation algorithm. Specifically, this is the heart of the algorithm. The beginning looks very much like what you saw already, which is take the derivative. What did I do here? Nope. The beginning looks like what you saw already. The derivative of the error, you write it down explicitly. You push the partial derivative inside the summation. You take the derivative of the square. Everything up to here is the same as in the linear network, until you get to this point, the derivative of the output of the network on a particular input number d with regard to a particular weight I. This is where we need to put the recursive algorithm. Before that, we're going to break down the output using the chain rule to the derivative of the output with regard to net times the derivative of the net with regard to the weight. The derivative of the net with regard to the weight, since the net is always defined as a linear sum, is simply the value of the corresponding xi. This is right here. So it's the same xi as the I in the weight. The derivative of the sigma with regard to the net, or the output with regard to the net, is the formula that I gave you, that I erased already. It's the formula that said that the derivative of a sigmoid is a sigmoid times 1 minus a sigmoid. So this gives you the full derivation of the gradient descent for a single sigmoid. Here is the recursive part. We start with the complete output. The k there is this unit here. We're assuming for simplicity there's a single output unit. And we calculate for it this value, which should look familiar to you from the derivative of a single sigmoid. This is the O times 1 minus O is the derivative of the sigmoid itself. And the t minus O is the part that comes from the linear, from before, from the very beginning of the derivation, because it's squared, it's 2 times t minus O. We call that the delta signal. This is the signal that gets propagated down from the top layers to each layer below it. So this kind of lambda is associated with will be associated with each unit in the network. We start with this one, using that formula. Then we use a recursive function to calculate the lambda values for each one of these based on the lambda values for this one and the weights. And then we use a recursive function to calculate the lambda values here. This is sometimes called the error signal. And the error signal propagates backwards in the network. You can think about it as the essential component of the derivative. So the error signal for any unit in the network corresponds to a summation, an implicit summation over all the paths that go from the top up to that point. And as you go down more and more layers, it's a summation over an exponential number of paths, exponential number of layers. This is the recursive formula. It says that the error signal for some unit is a weighted combination of the error signals of all the units in the layer above it, the layers to which it's connected. So the units for which it's connected. So you can study this on your own, make sense of it or not make sense of it. What's important from my point of view for you to understand is that this is solving, the conceptual part was done already. We know we're doing gradient descent. This is calculus. This is dynamic programming applied to calculus. This is not the heart of the machine learning part of it. The machine learning part of it is the inductive bias. But this is just to reassure us that we can run gradient descent. Why do we want to start with small weights? I'm sorry? It is the middle of the sigmoid function, that's true.
So if you have like a large weight, it would dominate the backpropagation.
If you have a large weight, it will dominate the backpropagation. I think that's true too. What does a network with very small weights compute? What kind of function does it compute? Go to the limit. What does a network with 0 weights compute? Zero weights. What function? I give you a network, let's say this network, and I tell you that all the weights are 0. The biases are 0, these weights are 0, everything is 0. What function does it calculate? 1/2. It's a constant. It would produce as output the constant 1/2, right? Because the net in is 0. Now, what if it's not? The weights are not. Let's say all these weights. Let's say just a single neuron. Let's talk for simplicity about a single neuron. Single sigmoid. We say that this sigmoid, it's a sigmoid, produces, if all of these are 0, it produces 1/2, constant. Y equals 1/2. What if they're not 0? What if they are just tiny, slightly different than 0? What function does it implement? Well, look at the sigmoid. This is the point of 0, right? 0 and 1/2. Linear function, very good. What happens is, if the weights are small, some of the weighted inputs is also very small. So it'll be around 0. If it's around 0, it's in this range right here. And in this range, the function is pretty much linear. I can stretch it. I can just show it maybe slightly better this way. This is also sigmoid. It's the same sigmoid. I just stretch the axis. In this range, around the 0 point, the function is very close to linear. In fact, if you take the derivative of the sigmoid at x equals 0, the derivative is flat. It's the point where the curvature changes. So right around the 0 point, there's an area of, well, theoretically, at the infinitely small neighborhood, there's an area of complete linearity, but practically it is almost linear. It's a pretty good approximation to linear for a while. Once you get to around here, maybe it starts curving, here it starts curving, but it's a pretty good approximation of linear. So by starting with small weights, you are starting with a linear function, or with an almost linear function. And as the weights get pushed by the gradient descent algorithm, the function becomes less linear. This is a form of soft bias. It says, prefer linear functions. Or at least start from linear functions and modify them minimally, gradually, to fit the data. That's a very nice bias, I think. Let's talk about networks that do classification in the minute we have. The simplest and most common way of doing classification with neural networks is produce not a single output, but multiple outputs, one for every class, for every category. And for every input, for a fixed set of weights, you propagate the output up. You get an output from each one of these. You check to see which one has the highest output, and you declare that the winner. That's called the winner-take-all networks. When you train these kind of networks, and you put in a training example with a particular category label, you put whichever one is the correct category label, you put a 1 here as the correct output, and you put 0 here in all the others. So when you train a classifier network, you train it with a label. The labels are now a set of, in this case, 5 labels, not a single one. It's 1 for the correct one and 0 for the others. Now, a sigmoid network will never produce zeros and ones, right? It only asymptotes towards them. So the output could get arbitrarily close to 1. The input, the labels are going to be actually 0 and 1. There's another way you can interpret this kind of networks, and that is, instead of doing a winner-take-all, you can say, you can normalize the output. Let's say the outputs here are some numbers, 0.9, 0.3, 0.2. You normalize them and you use that as a posterior. So you're saying that the outputs are proportional to the posterior over the labels. So you give back a distribution of possible labels rather than a single label. We might do the exam next time. I think you have enough to do your assignment. We're going to keep talking about neural networks for quite a bit more.